Okay, so we've just finished doing limits where x approaches a value, a number. Could be left-sided, right-sided, or two-sided. That's what we've seen in the previous couple lessons. The next lesson, so it's a little bit later in the book, but we'll go ahead and do it next because the first part of it, first several questions you're going to see are kind of a repeat of what you've done in the previous sections. And then there's some new stuff after that, a different type of limit that we'll talk about. But let's go ahead and look at these first, I believe, first 5 questions on your printout. These are things that you would have learned already in the previous 2 sections. Okay, so number 1 here, the limit is x approaches 7 for 89. Well, we learned previously that if we could plug in the number, so if I want to plug 7 into that function, there's no x to actually plug into, so you're still going to get 89. Now that was true for left, right, or two-sided limits, so that's technically the first case that we looked at. You can plug the number in and it spits a number out, you're finished. So in other words here, the y value, the limit, is 89. Okay, simple enough. Number 2, the lit as x approaches -7 for -39x. Same thing. If we can plug in the number and it spits out a number, we're finished. So if I plug in -7 for x, I've got -39 times -7. That's going to be positive 273. So simple enough. You can both of those, plug in a number, it spits out a number. That's all you've got to do. Okay, let's keep going here to number 3. The limit as x approaches -2 from the left for 18 minus x over -19x plus 2. Okay, same idea again. If we can plug in a number and it spits out a number, we're finished. So let's try that. So let's plug in -2. So 18 minus x is -2. Be careful with your parentheses. On bottom, -19, times -2 plus 2. And we'll go through and we'll calculate that. So on top, that's really 18 plus 2, which is 20. On bottom, -19 times -2 is 38. Plus 2 is going to be 40. Well, that actually simplifies to be 1/2. Okay, so same thing. Uglier function, but still the same idea. If you can plug the x value in and it gives you a y value, that's your limit. Okay, doesn't matter if we're talking about left-sided, right-sided, or two-sided. So 1, 2, and 3 there are basically all worked the same way. Plug in the number, it spits out a number. Alright, scrolling on down here, number 4, the limit as x approaches 0 from the right for x over -15x to the 5th plus 9x. Okay, so let's try the same thing. Let's plug in 0 for x. It's going to give us 0 on top. And then look at what happens if you plug in 0 on bottom. -15 times 0 to the 5th plus 9 times 0. Well, that's all going to be 0 on bottom. So I've got 0 over 0. Okay. When we covered the previous couple of sections, we had a special case. When you got 0 over 0, that's division by 0. It can't be a solution. This told us to factor and cancel. Okay. So it's going to be the same thing here. Okay, so let's do that. Go ahead and X that out because that's not a valid solution. Alright, let's try to factor. So the limit as x approaches 0 from the right. On top, x, there's really nothing else you can do to that. It's factored as far as could be factored. On bottom, what if we pulled out an x? Give us negative 15x to the fourth plus 9. Okay. And your x's will cancel out. So we factored and we canceled. Now remember what we talked about last time. If you cancel out that numerator, there's still an understood 1 up there. So don't forget about that. Alright, now plug in your number. Nothing to plug into on top, so you just got the 1. Plug in 0 for x on bottom. Negative 15 times 0 to the fourth plus 9. Well, negative 15 times 0 to the fourth is 0. Plus 9 is going to be 9. So we've got a solution of 1/9. Okay. So again, this is the same case we saw in the previous couple sections. When we get 0 over 0, that means we have a common factor on top and bottom. So we factor and we cancel. So we factored an x out on the bottom. It canceled with the x on top. Plugged into what was left over. And then number 5 here. Okay, limit as x approaches 0 from the right for negative 13x squared plus 11x over x. Okay, you can probably look at that and tell it's going to be 0 over 0, but let's go ahead and write it out if you don't notice it immediately. We plug in 0 for x. That's definitely going to be negative 13 times 0 squared is 0, 11 times 0 is 0. 0 plus 0 is 0, and the bottom is definitely 0. So again, that tells us to factor and cancel. Okay. Again, that's not a valid solution. Okay, so this time we can factor an x out on top. That'll leave us negative 13x plus 11. Still have that x on the bottom. So the x's can cancel again. Now, just like in the previous question, you still technically have a 1 on bottom. It was on top previously because the entire top got canceled out there. This is on bottom. But think about it, we don't really say divide by 1. Okay, there's no point in writing that. So really, you can just look at the numerator at this point. Plug in 0. Negative 13 times 0 plus 11. It's going to be 0 plus 11, which is 11. Okay, everybody, after you get past those first 5 or so questions in this section, which is kind of a review of what you've done before in the previous couple sections, you'll get to the new stuff. So the new stuff is called limits at infinity. In the book, this is the textbook here that we're looking at on the screen. You can get to this on the ebook on Hawks, or if you go in the Learn screen of this section on Hawks, you'll see pretty much the same thing. So you can get to those either way. But they're calling it limits of rational functions as x approaches positive or negative infinity. Okay, so first thing, a rational function, in its most basic form, a rational function is a fraction. Okay? Something with x over something with x. That's what we're calling a rational function. There's going to be 3 different cases with this. And the way this book, and most calculus books do it this way, they take the first case and then they kind of use it and manipulate things in the other cases to kind of make it match this first case. So we're going to start off with just a simple function 1 over x. Okay? As x increases without bound. What are they talking about when they say that? That means they're going to start off with x being relatively small, say 10. Then they're going to make it bigger, say 100, and bigger, 1,000, and bigger, 10,000, and bigger, 50,000, and bigger, 1,000,000, and so on forever. Okay? So if you plug 10 into 1 over x, you'll get 1/10. As a decimal, that's 0.1. Okay. If you plug 100 in for x, you'd get 1 over 100, which as a decimal, that's 0.01. If you plug 1,000 in for x, you get 1 over 1,000, which is 0.001. Okay. What's happening is this. As you plug these bigger and bigger numbers for x in, the overall value is getting smaller and smaller. It's actually getting closer and closer to 0. Okay, so they've kind of written it out as fractions here. You might want to look at it as decimals. It might be easier to see for some people. Put 1/10 in a calculator. 0.1, 1 over 100, 0.01, 1 over 1,000, 0.001, etc. As you get these bigger and bigger numbers on bottom, you get closer and closer and closer to 0. So we say the limit approaches 0. Okay. And the notation for limits, we'd say the limit as x approaches infinity for 1 over x equals 0. Now note, this would be the same thing if we went in the negative direction. Okay, so they're saying x going to negative infinity here. They didn't actually write down the work they did here, but instead of these x values all being positive, what if you made them all negative? So plug in negative 10, negative 100, negative 1,000, negative 10,000, etc. Well, then all these would just have negative signs. And they'd still be getting closer and closer to 0. They would just be negative values. Okay? As x gets bigger and bigger towards infinity, y gets closer and closer to 0. Okay. This is what the graph would look like if you ignore all the points they have listed there. What you're going to see, say take this part of the graph, it's going down and it turns and it's getting closer and closer and closer to the x-axis. Well, think about it. The x-axis is y equals 0. So it's getting closer and closer and closer to 0 as we go to the right forever. To the right forever is x approaching infinity. So the y value gets close to 0 as x gets bigger and bigger. And the same argument in reverse. If I get on this part of the graph and I go back towards negative infinity, the graph's getting closer and closer and closer to 0. Okay. Now let's apply that to something bigger. Instead of a simple function 1 over x, what if we had limit as x approaches infinity for 3x plus 5 over 2x minus 1? Okay. Now they've used a graphing utility here to kind of get a rough graph, and they've showed a little bit of a rough graph there on the screen. Not very good graph, but it would be a graph like you'd see on a graphing calculator. The idea here is there's going to be some horizontal line somewhere along where I'm running the little mouse hand. Some horizontal line, straight left and right, that going to the left, this graph gets closer and closer to. Going to the right, this graph gets closer and closer to. So how do we determine what that horizontal line is? Okay. What we'll do is, here's where they show the work. They'll try to manipulate this function and use what we already saw for the limit of like 1 over x. Okay. So looking at this, you have 3x, you have a term with no x's, and then on bottom you have a 2x, and you get a term with no x's. So the biggest exponent we see on an x is 1. These are x to the first and x to the first. So what they'll do is they'll go through and they'll divide every single term on both top and bottom by x to the first. And then they're going to simplify. So 3x over x, the x's cancel, it leaves you a 3. 5 over x doesn't simplify. Okay. On bottom, 2x over x, the x's cancel, it leaves you a 2. Minus 1 over x doesn't simplify. Alright, so you end up with 3 plus 5 over x over 2 minus 1 over x. Alright, we want to take the limit of all this stuff. Think about it on a term by term basis. Okay? Forget about, just look at the top here, forget about 5 over x for a second. If I just said the limit as x approaches infinity for 3, well, there's no x to plug into there. It's just the y value 3. So no matter what x I plug into, I'm always going to get 3. Okay? So we could say the limit of any number is that number. That was kind of the same thing you saw in the previous couple sections. Okay, so notice down here they've said that term's 3. Alright, now let's go to the next term, 5 over x. Well, that's similar to 1 over x, which we saw at the beginning of what I'm showing you in the book here. We said the limit as x approached infinity for 1 over x was 0. Well, in the grand scheme of things, 5 on top instead of 1 makes very little difference. As x gets bigger and bigger and bigger, this overall value for 5 over x is going to get closer and closer to 0. So it doesn't matter if it's a 5 instead of a 1, it's still something over x. So that limit is 0. Okay, and they made the same arguments on the bottom. So on the bottom, the first term is 2. There's no x to plug into there. So no matter what you plug in, you're always going to get 2. And then the last term, you have negative 1 over x. So you get, what, negative 0 instead of 0. Well, there's not really a negative 0, so we just say minus 0. And then calculate. You got 3 plus 0 over 2 minus 0. That's 3 halves. So we're going to say our limit is 3 halves. Well, that seemed like a lot of work to do that. So I'm going to skip down and go to the last pages you'll see in this section. They've got a summary for limits at infinity here. Now notice what they have written here. They've got a function, and then all the subscripts and exponents on top are in terms of n, and on bottom they're in terms of m. Okay. Case 1 for m equals n. So if my biggest exponent on top, n, is equal to my biggest exponent on bottom, m, then the limit's going to be a sub n over b sub m. Well, what are those? Those are actually the leading coefficients in the terms where you had the big exponents. This is going to be whatever these numbers are. Let's go back and compare that to what we just did. Okay, so here was the problem. Look right here where my little mouse hand is. So I've got 3x to the first, I've got 2x to the first. So 1 equals 1. These are equal exponents. What's the coefficient sitting in front of those terms? Well, a 3 on top and a 2 on bottom. So our final answer was 3 over 2. So that last page, they're trying to give you a quick way to look at the problem and immediately get a solution without having to go through and do all this division. Okay, so they're going to call that case 1 in the book. If the exponents are equal on a limit at infinity, you have the ratio of the leading coefficients, so 3 over 2 in this case. And speaking of that, let's go back up to the first problem we did. They didn't label it an example. They started with 1 over x, and then they let x get bigger and bigger and bigger. Let's look right here. So this is x to the first on the bottom, and I don't even have any x's on top. Okay? So I've got a bigger exponent on bottom here. Same thing with x going to negative infinity. X is to the first on bottom, you don't have an x on top. So it's bigger on bottom. These came out to 0. Okay, so that's actually another case that they're talking about. Look right here, case 2 for m greater than n. Again, m was on the bottom, n was on the top, m greater than n. So they're saying if the exponent on bottom is bigger than the top, you get 0. Automatic. Okay. So again, case 1, if the exponents are equal, you get the ratio of the leading coefficients. Case 2, if the exponent's bigger on bottom, then you automatically get 0. And in case 3 is going to be the only thing that's left over. That's going to be where basically the top is bigger than the bottom as far as the exponents go. And you can see what they're saying here. It's going to end up being plus or minus infinity. Let's look at an example like that. Here's one right here. Limit as x approaches negative infinity for x cubed plus x squared minus x plus 1 over x squared minus 4. Okay, so looking through here, you've got an x cubed on top, you've got an x squared on bottom. The way the book is showing this, they want to simplify everything and use that first example where the limit is at infinity of 1 over x was 0. They want to basically use that here. So they're going to take the thing with the biggest exponent, the x cubed, and divide every single term by x cubed. So they're doing that right here. All right, think of how it simplifies. X cubed over x cubed 1, x squared over x cubed is 1 over x. Negative x over x cubed is negative 1 over x squared. 1 over x cubed doesn't simplify, so just bring it down. And then they're also dividing by x cubed on the bottom. So x squared over x cubed is 1 over x. 4 over x cubed doesn't simplify. Okay. Actually, negative 4 over x cubed. All right. So think about what happens. For on top, for the first term, you have a 1. So the limit as x approaches anything of 1 is going to be 1. These other 3 terms on top all have bigger exponents on bottom. So they're all going to be 0. So you got 1 plus 0 minus 0 plus 0. That leaves you just 1 on the top overall. On the bottom down here, you've got 1 over x. So again, that's bigger on bottom. X is to the first on bottom. You don't have it on top at all. So that's going to be 0. And then negative 4 over x cubed. Same thing. You've got x cubed on the bottom. You don't have any x's at all on top. So that's going to be 0. So I got 0 minus 0, which is 0. Okay. Well, 1 over 0 can't be a solution. We know from middle school, or maybe even before that, that you can't divide by 0. Huh? Since 1 over 0 is undefined, the limit is either plus or minus infinity. But you have to figure out, is it plus or is it minus? Okay, so they're going about it a little bit different way than I'm going to show you in the example problems, but investigating the expression shows the highest power is x cubed. In other words, x cubed is your biggest thing, and it's on top. This will dominate for very large values of x and will be negative for negative values of x. Thus, the limit goes to negative infinity. So what are they saying there? They're basically saying this. X was sent to negative infinity here. So negative infinity cubed is negative infinity. Excuse me. That's going to be much larger than any other term. You know, infinity cubed is going to be way bigger than infinity squared. Okay. You can even make the same argument on the bottom. Negative infinity squared is going to be way bigger than negative 4. Okay, so negative infinity squared is positive infinity. Anything negative squared is going to be positive infinity. So I've got a negative infinity over a positive infinity. Which gives me negative infinity. Okay, I'll show you a little bit different way to look at that on the example problems we work here in a few minutes. But to summarize again, for limits at infinity, okay, not limits where x goes to a number. That's what we did in the previous couple of sections. This is limits at infinity. x going to either plus or minus infinity. 3 cases. If the exponents are equal, then you have the ratio of the leading coefficients. If the biggest exponent is on bottom, you automatically get 0. If the biggest exponent's on top, then you're going to get either plus or minus infinity, and you've got to figure out if it's plus or if it's minus. And again, I'll show you a simpler way to think about that when we do some example problems here in a minute. Okay, so now that we've seen the 3 cases of limits at infinity, let's look at some examples. So here in number 6, it's definitely a limit at infinity. X is going to positive infinity here. And if you look, you have negative 10x over negative 11x squared minus 2. So on top there, the exponent on x, it's understood to be a 1. We typically don't write exponents of 1, but that's an exponent of 1 on the top. So looking at this, you have a bigger exponent on the bottom. 2 is bigger than that 1. So this is going to be the bigger on bottom case. If it's bigger on bottom, you're automatically going to get 0. Okay. So again, very little work to show there. Here, number 7, again, definitely a limit at infinity. X is going to positive infinity here. Look at your big exponents. Let's not even read the whole function here. You've got an x squared on top, you've got an x squared on bottom. So you have a tie. So I'm going to call this exponents equal. And when that occurs, you just look at the ratio of the leading coefficients. So the leading coefficient on the top, where the x squared was, is going to be negative 2. And on the bottom, where the x squared was, your coefficient is going to be a 3. So you're going to have negative 2/3 there as your solution. Alright, pretty simple so far. Alright, let's look at number 8. Find the indicated limit if it exists. So you've got x going to negative infinity. Okay. And then looking at your big exponents, you've got a cubed on top and a squared on bottom. X cubed on top, x squared on bottom. So 3 is bigger than 2. So we would call this bigger on top. Alright, so we know the solution is either infinity or negative infinity in this case. So we've got to figure out which one it is. The easiest way to do that is just look at the terms where your biggest exponents are from. X cubed over x squared. Okay. And then think about plugging in either a positive or a negative number into it. How do I decide, should I plug in a positive number or a negative number? Well, it depends on what x is sent to. X is sent to negative infinity here. So let's plug a negative number into this. I'm just going to use negative 1. Okay. And calculate that. Negative 1 cubed is negative 1. On bottom, negative 1 squared is positive 1. So we get negative 1 as a value there. All that we really care about is that's a negative number. So that's going to tell us negative infinity. Okay. If the limit where x approaches positive infinity, the only thing I'd have done different is instead of plugging negative 1 in, I'd have plugged in positive 1. And I'd have got my sign. And so that's all you're trying to figure out in the bigger on top cases. Plus or minus infinity. Plus or minus is what you got to figure out. depending on what x is sent to. X was sent to a negative infinity in this case, so I plugged in a negative number for x. If x had been sent to positive infinity, I'd have plugged in a positive 1. And I calculate it, and depending on the sign, that tells me plus or minus infinity. Okay, and number 9 here, look at what they're asking. Notice this is x approaching 4. So this is not a limit at infinity. Okay. You've got to be careful with that. This is going to be the 3 rules we learned back in the previous 2 sections we covered. This is x approaching a number. Okay, not approaching infinity. Okay, so let me get rid of this and we can work it. Alright, so in those previous sections, again, we always try to just plug in the number. So if we try that here, that's going to give us 4 squared minus 7 times 4 plus 12 over 4 squared minus 16. And if you multiply out and add all this up, you're going to end up with 0 over 0. So remember, when we get 0 over 0, that means factor and cancel. Okay. Again, 0 over 0 is not a valid solution. Okay, so we got to factor and cancel here. Limit as x approaches 4. Okay, on top, x squared minus 7x plus 12. That's a trinomial. So we're going to have x times x to get x squared. So we need 2 numbers that add to negative 7 and multiply to positive 12. So negative 4 and negative 3 add up to negative 7, and negative 4 times negative 3 multiplies out to positive 12. So there's our factoring there. On the bottom, x squared minus 16, that's a difference of squares. So that's x plus 4 times x minus 4. Okay. And notice we've got something in common. X minus 4 on top and bottom, so those can be canceled. That leaves us x minus 3 over x plus 4. All we've got to do is plug in our number now. So 4 minus 3 over 4 plus 4 is going to give us 1 over 8 as a solution. Alright, let's move on down here to number 10. The limit as x approaches negative 5 from the left for 12x minus 18 over x plus 5. Okay, so not a limit at infinity. It's x approaching a number, negative 5 from the left in this case. So we want to think about our rules from, again, the previous 2 sections. I would go one step further here. You have 2 distinct terms in this question. So let's write this as 2 separate limits. In other words, we could say the limit as x approaches negative 5 from the left for 12x plus the limit as x approaches negative 5 for the left from the left of negative 18 over x plus 5. Okay. So again, you can break it apart like that because it's multiple terms. The reason I did this, it's going to make it a little easier to look at. The first limit over here, you're able to just plug negative 5 in for x and calculate that. So you'd have 12 times negative 5 there. That's going to be negative 60. Okay, so you've got that one. We've still got to do the other limit though. Alright, so on this, if we plug in negative 5, we'd have negative 18 over negative 5 plus 5. Should be negative 18 over 0. Okay, so that's a non-zero number over 0. We dealt with that already in the previous couple sections. When we see this, then for a left or right-sided limit, which this is a left-sided limit, then we know we have a solution of either negative infinity or positive infinity. And you had to figure out plus or minus. So let's do that. The easiest way to think about it, since this is left-sided, I want to pick something just to the left of -5. So on a number line, if I look at -5 and I move 1 unit to the left, I'd be at -6. So let's think about plugging -6 in here. Okay, it goes -18 over -1, which is positive 18. So since this is positive, that means I know my solution's positive infinity there. So we're going to have this plus infinity. Go ahead and bring it down. Alright, so here's the thing. We've got -60 plus infinity. Infinity is a concept. You can never actually get to it. So it doesn't really matter if we add or subtract anything from it. It's still so large that we're never going to get there. So -60 plus infinity is just plus infinity. Okay. More specifically, I would just answer it as infinity. Okay. Let's keep going. All right, number 11. Find the indicated limit if it exists. The limit as x approaches infinity. So there we go. We're back to limits at infinity again. So that's the new rules that you just learned in this section for -5 plus 11 over x cubed. Okay. Well, when we taught you the 3 rules that you learned in this section, pretty much all the problems were something over something. Some sort of fraction. Well, this has 2 separate terms. It's got a number and then it's got a plus a fraction over here. Well, why don't we make it look the same as the rules? To me, that's the easiest thing to do. So, not that there aren't other ways to do it, but I think this is the easiest. So what I want to do is I want to rewrite -5 as something with a denominator of x cubed. Okay, so I've got -5 here, and I want to get an x cubed on the bottom. So how can I do that? Well, if I put it there, if I put the x cubed also on top, effectively what have I done? X cubed divided by x cubed is 1. -5 times 1 is still -5. So I haven't changed the value of it. I've just gotten a common denominator. Now that I have a common denominator, I can write it all together as one fraction. Okay. All right, so now it looks like one of those 3 rules we dealt with. Okay, so we're supposed to look at our exponents. So biggest exponent is 3 on the top and bottom. So we do the ratio of the leading coefficients. So we've got a -5 on top, and we've got what sitting in front of x here on bottom? Well, technically there's a 1 there. So you've got, in other words, -5 over 1, or in other words, just -5 as your solution. Okay. All right, number 12, again, limit at infinity. X is going to negative infinity this time. Look at your big exponents. Again, we've got 2 on the top, 2 on the bottom. So this is exponents equal again. So look at the ratio of the leading coefficients. -3 over 19. So again, as you can see, on these limits at infinity, there's not a lot of work. You just got to know the rule. That's 3 cases. You got to know when to apply each case. All right, number 13 here. Limit as x approaches negative infinity. So limit at infinity again. So look at your big exponents, 2 on the top, 3 on the bottom. So this is bigger on bottom, means you get 0. No work to show. Alright, then let's get down here to this piecewise function. So this is not a limit at infinity. Its limit as x approaches a number, -5, and they're actually going to ask us to do it left-sided in step 1, right-sided in step 2, and two-sided in step 3. So remember, this was again what we did previously in previous sections. Left-sided limits go with the less than sign. So less than is left-sided. So we should be plugging -5 into that top piece. Okay, calculate that. That's going to be what? 25 minus 50 plus 34. That's going to be what, 9? Okay, so there's our left-sided limit. Step 2 is the right-sided limit. So remember, the greater than sign is right-sided. Okay, so we should be plugging into the bottom piece here. This will be 10x, x is -5, plus 59. So that's -50 plus 59, which is also 9. Alright, and then lastly, the two-sided limit. The two-sided limit, you can look at your left and right-sided limits to determine your two-sided limit. The left and right-sided were both the same, so that means your two-sided limit is the same. Okay, simple enough.